Welcome to our lesson today, mathletes. So this is our last lesson in chapter 2, and we're going to continue our investigation of continuity. And this time we're going to talk about the intermediate value theorem. Okay. And by the way, you can use IVT as an abbreviation for the intermediate value theorem anytime on a test or things like that, okay, if you have to cite it. All right, so the intermediate value theorem. So it says let f be continuous over a closed bounded interval from a to b. So let me mention a couple of things. First of all, when you have a closed and bounded interval, that means that you have two real endpoints. Okay, so in other words, it's not going to go to infinity or things like that, right? And closed is when we use the brackets. Okay, if I say like from 2 to 3 with brackets, that's an infinite set of numbers, right? From 2 to 3, because I have like 2.1, 2.11, 2.111, 2. And we can play that game forever, right? We can do the same thing for any. We can say 2.1, 2.12, 2.123, 2.1234, and we can play those kind of games forever. So there's an infinite amount of numbers in this interval, but what's closed about it is the fact that we actually stop at 2, right? Like if I go to the left and 2 is included, if I have this interval here from 2 to 3, then 2 is the stopping point. There's a definitive stopping point on the left, which is 2. Same thing on the right, right? I don't go past 3. I stop exactly at 3. If you had this interval, 2 to 3 like this is called an open interval. Because let's say I was getting closer and closer to 2 on this side. Well, I could have 2.1, 2.01, 2.001, 2.00001, right? So there's not really a definitive stopping point because I can always find a number between 2 and whatever number you give me, right? Even if you give me 2.1 or 2.00, like let's say you give me a million zeros and then a 1, right? A million zeros and then a 1. I could just give you 2.101 zeros and then put a 1 after it, and that's between what you gave me and what and 2, right? So when you have parentheses here, that means you get as close as you can to 2 without actually reaching it, and that means you can always get a little bit closer, right? And so it's an open interval. Okay, so this is called an open interval, and this is called a closed interval. And the reason I want to spend a little time on this is because you'll see that kind of come up in a lot of definitions that we'll see here and there in theorems and such. And so I think it's just a good thing to remember. So closed interval is where you have brackets or where you have included endpoints, and open intervals are where you have parentheses or where you have endpoints that are approached but not reached, right? Where you have endpoints that are not included in the interval. Okay. All right. So that's what this says is that the function is continuous on this whole interval from A all the way to B. Okay, including those endpoints. All right. Then they say if Z is a real number between f of A and f of B. Okay. So they're saying if we have a value that's between the output of the left end of the interval and the output of the right end of the interval, right? That's what f of A and f of B are. Then there's a number C in A and B, so there's a number C that's between A and B that satisfies this condition that where you have, okay, well, there has to be a value or input C that gives you this output Z. Okay? All right, now if that didn't make any sense, don't worry about it. Let's look at it graphically, okay? And I'll show you another argument to hopefully make this a little more clear, okay? So basically, if we have an interval from A to B, right, where those values are included, then remember that if a function is continuous over this whole interval from A to B, that means when I'm tracing from A to B, I can't pick my pencil up off the graph, right? So if there's a value between f of A and f of B that we call z right here, then there's no way I can get from f of A right here, right, to f of B without passing z, right? If I can't pick my paper or my pencil up off the paper because this is a continuous function, I have to not only pass z, but I have to pass every number from f of A to f of B, right? Okay, and so that's the argument here, is saying that, okay, well, if there's something between f of A and f of B and we call it z, then that means that I have to cross that point at sometime between f of A and f of B. And that means on the x-axis from A to B, there has to be some input C that gets us the output of Z, right? And so that's all that's saying. So it's a lot of these, sometimes these theorems, we use a lot of kind of technical language and it makes it a little more confusing, but it's also like, if you kind of look at the visual and think about it intuitively, it's kind of an obvious statement, right? You're just saying, hey, if we have something that's continuous all the way from here to here, then wherever I start and between wherever I start and wherever I end, there has to be a value, I have to reach all those points in between, right, on my output side. And so there has to be an input that gets me to any of those outputs in between, right? So that's all that's saying. All right, so let me show you another representation of this. So here I'm starting with this interval A to B, right? Okay, so I have this interval here from A to B, and I'm just picking specific numbers, but you can put any numbers to this, right? So you can see A is 2 and B is 9, right? And then I have f of A and f of B. And what I did is I switched these up to where f of B is on the bottom just to mix it up a little bit. So here f of A is higher than f of B. So if I'm saying, so this is the range, right? So I have this domain interval and I have this range interval. And so if I'm saying that f of x is this continuous function from A to B, then like think about how to get from here to here. If it's continuous, once again, I can't pick my pencil up off the paper. So I have to get from here to here, right? And if I go from there to there without picking my pencil up, I have to cross all these values. And for any of these values, there has to be one of these values that gets me one of these outputs, right? There has to be one of these inputs that gets me one of these outputs. Okay. Now I wanted to show you this because that was one way to get there, right? I could also get there like this, right? I could also get there like this. I could also get there like this, right? There's a lot of ways to get from point A to point B, but at some point I would have to cross all of these outputs, right? And there would have to be one of these inputs that gets me to that. Now, what the theorem doesn't tell us is it doesn't tell us whether we go above the limits of f of A and f of B, right? Like we could go above and below and get back there, right? It doesn't tell us how many times that maybe we get to that z value. Like let's say z is 6. Like z could occur twice, right? Or maybe 3 times or 5 times or 1,000,000 times, right? So we don't know how many times it exists or how many times we cross that value, but we know we have to get there. We have to pass it at least once to get from here to here, right? And so, all right, so that's all this is saying, is we can't conclude that, it's not going to go above or beyond the values that we have, right? We can't conclude that. We can't conclude how many times we're going to reach that z value, okay? all we can conclude is that we have to pass that z value at least once, and there has to be some input, and we call that input c, that gets us to that output z. Okay.